All right, then let's talk about the Lewis theory of acids and bases. We're going to be kind of general with this. We're not going to get as specific with this as we do with Arrhenius or Bronsted-Lowry. In fact, most of this unit on acids and base theory, acids and bases theory, or acid-base theory, is going to be centered around Bronsted-Lowry. Okay? We'll kind of go back and forth between Arrhenius and Bronsted-Lowry. We're not going to spend a lot of time with Lewis theory, and that's our next theory of acids. But as we introduced in the at the end of the Bronsted-Lowry video, Lewis theory kind of deals with those Lewis dots. Same guy. Okay? Well, Lewis's definition of acid bases, let me back up a minute and tell you why he felt there was another need or need for a different acid-base theory. There are certain salts, okay, that don't have any protons and don't have any hydroxides that behave, when you put them in water, create a solution that behaves like an acid or like a base. So if we have salts that behave like an acid or a base, and there's no hydrogens in the formulas anyway, no hydroxides in the formulas, we can't use Bronsted-Lowry to really explain what's going on. Does that make sense? So he used, guess what?
Krypton.
What was his drawings about? Dots, which represented electrons, valence electrons. So he was talking about the way electrons behave. Okay? Very good. Did you read ahead or something? It's not, well, acids actually accept electrons.
Question, how could one read ahead?
Really? You're really going to ask? There you go. Who said that? All right. It's on the website. Okay? But if you put all the pamphlets together, you get a book. Come on. Give me a break. Well, let's see. It's about like that. No, it isn't. Really. No, the packets, the largest packets are about like this. So if I only got 10 packets, what's it going to, I mean, some of them are bigger than others. It really only comes about like that. You think so? All right. I hear you. I wanted to have to print it out just to show you. Huh? Wait. It accepts a pair of electrons, actually, I think it is. Okay? Y'all got to stop talking, let me think, so I can get the definition right. Yeah, I'm looking like I'm playing Tetris, right? Okay. All right. Accept a pair of electrons in a covalent bond. And bases are the opposite. Yes, it is a hardcore definition. Right. Hardcore. So going back to the end of our discussion of Bronsted-Lowry, we made that sort of transition between the two. We had a hydrogen ion. We had a water molecule written out in a Lewis dot form. We had the hydrogen ion joining up with that one of the lone pair electrons in the water, and as a result we formed H3O plus which we could have written as all right, those being pretty much the same thing there at the end. Okay? So, what species here accepted a pair of electrons in a covalent bond? A or B? Accepted a pair of electrons. A. This didn't have any pair of electrons. It accepted this pair into this covalent bond right here. See it? Okay. So this is our Lewis acid. Okay. And what species donated a pair of electrons to a covalent bond? It didn't give them up. It just shared that pair of electrons. I could have said shared. Okay. Shares a pair of electrons to a covalent or in a covalent bond. Okay. Another way of saying it. All right. What species shared a pair of electrons in a covalent bond? The H2O. So this is our Lewis base. Okay? Huh? And we're done for today? Really?
Heck yeah.
No, time's not up yet.
It's like the Stewards class. I'm going to go to lunch early.
I might get in trouble for sitting down there. What?
Steward does it.
Okay. Acids are any species that accept a pair of electrons. Well, the hydrogen ion accepted that pair of electrons into this covalent bond. It did accept the hydrogen. If I were using the Bronsted-Lowry theory, that's what we use as our definition of a base. Okay, now listen. Anything that accepts a proton, according to Bronsted-Lowry, anything that accepts a proton is a base, right? By the same definition, this is a base. This is a Bronsted-Lowry base because it accepted this proton. All right? Anything that donated a proton, according to Bronsted-Lowry, is an acid. Lewis says this is the acid. Now, here's the tricky part, and I don't think it's tricky at all if you just stop and think. So give me full attention here, okay? It's not just this that's the Lewis acid. It's anything that gave this to do the accepting of the pair of electrons. So HCl, okay, could have been the species that gave up that hydrogen ion that did this, right? That makes this the Lewis acid too, because that's where it came from. All right? So anything that hold on, listen, what? No.
It technically accepted an electron from water, so therefore HCl is the acid, according to Lewis.
It's a bit more complex in that the hydrogen ion is what is the, strictly according to this definition here, the hydrogen ion is the Lewis acid. But the species it comes from is also the acid. Okay? No? Don't get it? Alright. That's the class with it?
Yeah.
So who's doing the accepting and who's doing the donating?
Well, the Lewis base is donating or sharing this pair of electrons with this hydrogen. If it has an electron pair that it's going to share or donate to a bond, that's the base.
Okay, so it is.
This is the base.
Sharing and donating.
Well, they're kind of synonymous in this context. In the context, as I understand it, as I would explain it and whether I understand it, the way it works. All right, listen, guys. Y'all are chatting a little bit. We're trying to deepen our understanding so you got a good idea about this stuff, okay? So please focus here a minute, all right? I know you want to go to lunch early. Ain't going to happen. But, but we want to make sure you're clear about this before you leave. Okay? Go ahead, Brooke.
So the hydrogen accepted that they were donating.
Yeah, this pair of electrons right here is being donated to a covalent bond. It was a lone pair, and now it's not going to be a lone pair because it's being donated to a covalent bond. So that makes this species the Lewis base. The hydrogen ion is going to accept that pair of electrons in a covalent bond. So it joins up in a covalent bond with a pair of electrons it never had to start with.
Okay.
So that makes that the acid, and the species that the hydrogen ion came from is also the acid. Okay? Yes.
How many arrows did you have to draw to get that good at drawing arrows?
What?
How many arrows did you have to draw to get that good at drawing arrows?
The question is, how many arrows did I have to draw to get that good at drawing arrows?
Crafty looking compared to yours.
Yeah, you know, I used to be crappy at drawing arrows too. I had a friend of mine who was an engineer who drew this really nice arrows to explain progress in what he was doing. And I just started working it. I am serious. Yeah. He was born in Germany and actually got a job with BMW, you know, so it's really cool. Anyway, now, this actually expands the definition of an acid greatly. I thought he did a good job. I started trying to follow his pattern. That's all. That's all there is to the story. It's not that big a deal.
You're a copycat.
Yeah, I'm a copycat.
Do you go home and draw arrows?
Yeah.
Really?
Now,
No.
let's take a minute.
That's
Let's look at your solubility rules. Okay? Tell me one of the ions that is generally insoluble. One ion. Any ion that's generally insoluble. Really? You're supposed to memorize at least those 12 ions. Huh? Phosphate is generally insoluble. Okay?
ammonia. Hydroxide. No.
Phosphate.
Ammonia.
What is the charge on a phosphate? All right, so this is really a little bit of an over. It's not really what a phosphate is, but I'm going to simplify it for this purpose, okay? And it has 3 negative charges, right? So there's 3 extra electrons on here somewhere. Now I don't count them, but I think this is right. Okay? So when phosphate joins up with something, it's going to be insoluble, correct? What does it join up with? What does it phosphates join up with that makes it insoluble? Huh? What?
I don't know what you're asking. Like, what's the question?
With solubility rules.
Alright.
Most phosphates are insoluble, correct?
Yeah.
Okay, so what can I put this with that would make it an insoluble substance? Not sodium, because sodium phosphates are soluble. What would make it insoluble?
Anything but group 1 and ammonium.
Anything but group 1. So pick one. Anything that's not group 1 or ammonium.
Lead.
Iron.
Lead. Lead would definitely be it. Okay, let's use lead 2. Lead 2. Yes. Yep. Okay. Now, I'm not going to try to balance the formula because we'd have 3 leads and 2 phosphates, okay? But we're going to keep this really, really simple. Which one of these two is donating a pair of electrons to a covalent bond to form a solid? The phosphate. Which one's going to accept that pair of electrons?
The lead.
There's your acid base right there. What? You get it?
No, I don't get it.
Okay.
The positive ones always accept, the negative ones always give.
How about we do just copper 1? That's a little bit easier to see.
It's going to be krypton?
No, because krypton doesn't form ions. It's a noble gas.
Is it really?
What? Unless you're reading a DC comic book, krypton is a noble gas. If you're reading DC Comics, what is krypton?
What makes
A planet. Actually, it's not a planet anymore because it exploded. So copper 1, if I have 3 negative charges on here, somewhere. This copper can join up somewhere. Okay, it accepts a pair of electrons, actually 3 different coppers, not just one copper. It's going to accept a pair of electrons. The phosphate is donating a pair of electrons to a covalent bond, potentially. Okay? Which one's the base? The phosphate's the base. So anything it came from is the base. What's the acid? The copper, and anything it came from is the acid. So if we started out with copper 1 chloride, that's also the acid because that's the acid.
So because phosphate is negative, it's going to accept, so that would not make it base?
No, it's going to, because it's going to share this pair of electrons with something else. It brought the electron. Look, if it brings the electrons to the party, it's the base.
In other words, if it's negative, that means it's giving away electrons.
Yeah, I understand.
If it brings the electrons to the party, yeah, it's the base.
So it's the designated driver.
It's the, okay. If you want to call it a designated driver, that's great. All right. Got it? Now look, we are not going to be doing equations and things like that. Listen, please. Listen, please. We're not going to be doing equations and things with Lewis acids and bases. All right? That's a little beyond the scope of the class. It's not beyond the scope of the class for you to be able to describe the theory and show how it might work in certain contexts. Okay? Just with equations. All right? All right.
Okay. Can you just I'm going to take a picture.
Just go back and look at the video I did, if you want to review, on Bronsted-Lowry. Follow the example.
Can you just email that?
I usually do, but I can't promise that I will. I never promise.
You have it.
I love your email about Mother's Day.
You like that?
Yeah, I saw that. I think he made fun of you for that.
What? Why? Don't you think mothers deserve to be recognized on Mother's Day?
You sending out the email is why we made it.
Look, a lot of students forget their mothers on Mother's Day.
Isn't it before I did it?
You know? Ask your mama whether it was hilarious or not.
My mom thought it was pretty amusing, actually.
Oh, really? Oh, man, here I'm trying to help you out.
I didn't tell my mom about it.
Okay.
About what?
Now, I know most of you in here probably wouldn't forget your mama on Mama's Day, but I've had a lot of students that didn't care. And I'm just saying, you know, you shouldn't forget your mama on Mama's Day.
What you're supposed to do is act like you forgot about it and then, like, surprise them.
No, because then they're in its own mood, and when you surprise them, it's not going to make it better.
Yeah, it is.
Oh, we just learned more about your mother than we want to know.
When my mom gets in her bad mood, I can't do anything to make her happy.
What is it they say? When Mama's unhappy, everybody's unhappy.
Yeah.
Give her chocolate.
Wait, so where do we find this Bronsted?
If she's mad.
What? All these notes I gave you on Bronsted-Lowry?
Question.
Well, which one is it?
Huh?
There's so many. Which one's it?
Yeah.
I don't know the number.
Which one is
I don't even know what.
which one is what, Brooke?
What?
Which one is what? You said which one is it? Which one is what? Okay, I stated when we were going over this that this is an example of a dissociation equation for the Bronsted-Lowry theory of acids and bases. So you're going to transfer this knowledge